Hi, this is Dr. James Wood, and welcome to today's lecture. It's Class 19 in Statistical Methods, entitled Introduction to Probability. Now, let's take a moment to see where we are in the course. You've now completed 2 midterm exams and 2/3 of the class, and you've learned a great deal. During the remaining weeks of the class, you're still going to have to work hard, but many students have told me that the last part of the class seems easier than what has gone before. Beginning with the next lecture, we're going to be talking about political polls and surveys. And to understand that topic, you're going to need to know something about probability. So today we're going to be covering some basic ideas in probability theory. Probability theory provides the mathematical basis for statistics, or put another way, probability theory is the mathematical, concrete foundation on which the house of statistics stands. Algebra, calculus, and probability theory are probably the 3 most important math discoveries since the time of ancient Greece. Now, the Greeks were geniuses at geometry, but they didn't have algebra, calculus, or probability theory. Algebra was developed about 800 years after Christ by the Iranian mathematician Al-Khwarizmi, and calculus and probability theory were developed in Europe about 800 years later in the 1600s. I think I said in Europe, right? Okay. Now, in the 1600s, about the time that the Pilgrims were landing in America, some noblemen in France who were big gamblers had a disagreement about what the odds should be for certain games of dice. They paid some of the leading mathematicians of the day to look into the problem. One of these was the French mathematician Blaise Pascal. Pascal developed some sophisticated mathematical theories to explain the odds in dice games and card games, and his work became the foundation of the modern theory of probability. Pascal was a very interesting person. Not only was he a great mathematician, he was also a great philosopher. And he was a great scientist and performed the first known controlled experiment. In addition, Pascal was very religious. He was deeply affected by a mystical experience he had of God. He said many famous things, and you can find them on the internet. And here's one. Love has reasons which reason cannot understand. Pascal is saying that love knows more than reason knows and more than reason can ever know. Not exactly what you might expect from a mathematician, but he was a lot more than a mathematician. During the past few centuries, probability theory has had an enormous impact in many fields of human life. Let me give you a few examples. Probability theory continues to be applied to gambling games like craps and poker. If you want to be an expert gambler, you have to know about probability theory. All the state lotteries have been thoroughly analyzed using probability theory. For instance, the state of Texas hires experts in probability to help it figure out how to design its lottery games so that the state always ends up making money. There have been cases, by the way, in which states misestimated the probabilities in lottery games and ended up losing millions of dollars. Risk theory, which is a branch of probability theory, is an important part of public health studies on smoking. Studies on smoking in the 1950s and 60s made clear that the probabilities of lung cancer, emphysema, and heart disease are substantially increased by smoking. And that's why there were and are big public campaigns to discourage people from smoking. Studies in the 1950s and 60s made clear that seatbelts substantially reduce the risk of death and injury in car accidents. And that's why laws were eventually passed requiring the installation of seatbelts in cars. As I said earlier, probability theory is also the mathematical foundation for statistics. Now, you've already encountered probability in this class when you learned about density histograms, which give us a way to picture probabilities and understand them. During the coming weeks, you're going to learn a lot about political polls and surveys of political opinion. Polls and surveys are based on probability theory. Toward the end of this semester, you'll be learning about something called inferential statistics. You'll learn about a procedure called the t-test. And if you go on to advanced statistics, you'll learn about a procedure called ANOVA. These are all based on probability theory. So now let's talk about what statistics deals with. Statistics has been called the science of uncertainty. Science seeks knowledge that is certain or nearly certain, so it sounds almost like a contradiction to talk about a science of uncertainty. What could that mean? Well, let me give you a famous example. It involves the probability of being kicked to death by a horse. In the late 1800s, before the invention of cars, armies didn't get around in tanks or Humvees. They used horses. And every once in a while, some soldier would be saddling a horse or walking behind a horse, and the horse would suddenly kick him, causing his death. Now, being kicked to death by a horse is about as unpredictable an event as you can imagine. It's rare, and in an army where everybody was working with horses, it was unpredictable who would get kicked by a horse or when. But a mathematician who lived at the end of the 1800s had a theory that rare events often follow what is called a Poisson distribution, the normal distribution. But the Poisson distribution and the normal distribution have different shapes. Now, this is a Poisson distribution, and you can see that it is not symmetric. It's not bell-shaped like the normal curve. The mathematician obtained records of the number of soldiers in the various corps of the Prussian army who had been kicked to death by horses during a 20-year period. And here's a graph of what he found. The green bars are the mathematician's predictions based on the Poisson distribution. The green bars indicate that according to the mathematician's prediction, there should be almost 100 times that one soldier in a corps was killed by a horse kick. There should be about 30 times when 2 soldiers in a corps were killed by a horse kick. And there should be about 10 times when 3 soldiers in a corps were killed by a horse kick. Now, the blue bars indicate the number of soldiers in the Prussian Army Corps who were actually killed by a horse kick during the 20-year period. For example, in almost 100 cases, 1 soldier in a corps was killed by a horse kick, and so on. So you can see that the green and blue bars are very similar in shape, and they follow a similar pattern. And this indicates that the actual death counts followed the Poisson distribution very closely. The mathematicians' predictions were right. This rare event of being kicked by a horse did follow the Poisson distribution very well. Now, this example illustrates how there can be such a thing as a science of uncertainty. There was complete uncertainty about which individual soldiers would die. But there was near certainty about the group pattern. The number of deaths in each Army Corps followed a Poisson distribution, just as the mathematician predicted. So this is how statistics can be certain about uncertainty. It can predict that even uncertain events will follow a predictable pattern. Mathematicians have several definitions of probability, but the definition most commonly used is called the frequentist definition. The word frequentist refers to the frequency with which an event occurs. And here's how the definition works. We begin with some procedure, event, or situation that's repeated many, many times. Each repetition of the procedure, event, or situation is called a trial. As an example, let's say that a coin is tossed thousands of times. So flipping the coin is the procedure or event that's repeated many times. Each coin flip is a trial. In the second part of the frequentist definition, each trial has one or more possible outcomes. Of the coin flip, there are 2 possible outcomes, heads or tails. In the third part of the frequentist definition, we say that each outcome occurs in a certain percentage of trials. So, in our example, when we toss the coin thousands of times, we find that heads comes up 50% of the time. The percentage of trials that an outcome occurs is the probability of the outcome, according to the frequentist definition of probability. So in our example, because heads comes up in 50% of the coin flips, we say that the probability of heads is 50% or 0.50. Probabilities tend to be written as decimals, like 0.50, but when we're talking, a lot of times we use percentages. So as you see, according to the frequentist definition of probability, the probability of an outcome depends on the frequency of the outcome in a large number of trials. And that's why this definition is called the frequentist definition. So let's look at another example, this one using dice, to see how the frequentist definition works. You roll one die. Now, a die, two of them are dice, but one of them is called a die. So let's suppose you roll one die, and you want to know what is the probability of rolling a 6. Now, according to the frequentist definition, we begin with some procedure, event, or situation that's repeated many times, with each repetition called a trial. So in this dice example, stop and think for a second. What's the procedure or event that's repeated multiple times? I'll give you a few seconds to think about it. Okay, now in this example, the event that's repeated over and over is rolling a single die. And in this example, each roll of the die is a trial. In the frequentist definition, each trial has one or more possible outcomes. So in the dice example, take a moment and ask yourself, what are the possible outcomes of a trial, of rolling a die? Okay, the possible outcomes of rolling a die are rolling a 1, rolling a 2, rolling a 3, rolling a 4, rolling a 5, or rolling a 6. So there are 6 possible outcomes of rolling a die. Each outcome occurs in a certain percentage of trials. So in the dice example, in what percentage of trials does a 6 come up? Take a second to think. Okay, here's the answer. If it's a fair die, then a 6 comes up 16.6% of the times. And here's how we arrive at that number. There are 6 sides, and if it's a fair die, then each side comes up 1 out of 6 times when we roll again and again and again. So the percentage of times that we roll a 6 is 1 out of 6, and that's the same as 1/6 or 16.6%. Okay, 16.6%. Okay, in the frequentist definition, the percentage of trials that an outcome occurs is the probability of the outcome. So in this example, what is the probability of rolling a 6? Give you a second to think about it. Okay, the probability is the same as the percentage that it shows up. That's part of the frequentist definition. So the probability is 16.6%, or if we wanted to say it, 0.166. What a probability is, at least according to the frequentist definition, let's talk about some of the basic ideas of probability theory. First, we'll need to learn some new mathematical notation. In statistics, a capital P followed by something in parentheses is shorthand for the probability of whatever is inside the parentheses. For instance, P followed by an A with the A in parentheses means the probability of A. We're assuming here that A is a possible outcome of a trial. As another example, we can write capital P followed by the word heads, with heads inside of the parentheses. These symbols mean the probability of heads in a coin flip. Or this notation means the probability of tails in a coin flip. If we're really economical, we can write the probability of heads like this, with just an H representing heads. Of course, if we write P of H like this, we have to let other people know what the H stands for. Or here's another example, where you just use one letter T to stand for tails. So to sum up, we can put any outcome inside the parentheses that we want when we want to represent the probability of that outcome. Now, during the next few weeks, we're going to focus on dichotomous variables. So let's talk about the probability of dichotomous variables. As you recall, from the beginning of the semester, a dichotomous variable is a variable with two possible values. A dichotomous variable is also known as a binary variable. We can treat the values of a dichotomous variable as two outcomes, each with its own probability. Now, here are some examples of dichotomous outcomes and their values. When we flip a coin, there is the probability of heads or the probability of tails. It's dichotomous, two outcomes. When we answer a yes-no question on a test, there's the probability of the answer being yes or the probability of it being no. When we die, there's the probability of enjoying happiness in heaven or the probability of suffering for eternity in hell. Now, to simplify matters, we can use the letter A to represent one outcome and the symbol B to represent the other. And that's what we'll do in much of this lecture, using A and B to represent the two possible values or outcomes of a dichotomous variable. So, in most of this lecture, we'll let A be one of the outcomes. For example, A might represent heads in a coin flip, or yes on a test question. And we'll let B be the other outcome. For example, B might represent tails, or that's on a coin flip, or no on a test question. We'll use this notation, the probability of A, to represent the probability of the first outcome. And we'll use this notation, the probability of B, to represent the probability of the other outcome. We'll use the lowercase letter p to represent the value of the probability of A. So, if the probability of A equals 0.75, then we say that little p is 0.75. That little p stands for probability. They just use a lowercase to keep it straight from the big P, which also means probability, but is used differently. Now, we'll also be using the lowercase letter q to represent the value of the probability of B, the other outcome. So if the probability of B equals 0.25, then we say that Q is 0.25. Now, a basic feature of P is that it's always between 0 and 1, and so is Q. So I've written the mathematical notation up here. 0 is less than or equal to P, which is less than or equal to 1. Similarly, 0 is less than or equal to Q, which is less than or equal to 1. So we're never going to have a P or a Q that's greater than 1. And we'll never have a negative P or Q. Both of them are always positive and always between 0 and 1. Actually, they're not always positive. If they're 0, they're what we call non-negative, but you know what I mean. Now, if P is equal to 1, that tells us that the outcome A is certain to happen. Now, maybe you have heard the saying that nothing is certain in life except death and taxes. Another way of saying the same thing is that the probability of death is 1 and the probability of taxes is also 1. If P is equal to 0, then outcome A never happens. You've probably heard a person saying something like, "I'll vote for Ted Cruz when hell freezes over." Now, another way of saying the same thing is that the probability of hell freezing over is 0, and the probability of that person voting for Ted Cruz is also 0. Now, probabilities between 0 and 1 mean that the outcomes sometimes happen, but not always. The closer P is to 1, that means the more likely it is to happen. The closer that P is to 0, it means the less likely it is to happen. A probability of 0.95 is getting pretty close to 1, and so it means that outcome A is very likely to happen. Remember, according to the frequentist definition, it happens on 95% of trials, but it's not certain. 0.95 is not 1. 1 is certainty. 0.95 is almost certain, but not quite. A probability of 0.50 means outcome A is as likely to happen as not happen. For instance, if you flip a coin, the probability of getting heads is 0.50, or we usually say 50%. That means the outcome is as likely to be heads as it is tails. A probability of 0.05 means the outcome is very unlikely to happen. It's rare. It's almost zero, but not quite. It could happen, but unlikely. Now, here is one of the most important facts to remember about P and Q. P plus Q always equals 1. That is, if there are two possible outcomes, and the probability of the first outcome is P, and the probability of the second outcome is Q, then P plus Q equals 1. That tells us that either P or Q is going to happen. It's certain that P or Q happens, but, A or B will happen. It's certain that A or B will happen, but it's not certain that A will happen or that B will happen. It's them together. We're sure there will be some outcome. Here's our example. Suppose we're flipping a coin and the coin is fair. Then the probability of getting the first outcome, heads, is P, and P is equal to 0.50. There is only one other possible outcome, getting tails. The probability of this second outcome, getting tails, is Q, and Q is also equal to 0.50. When we add P and Q together, we get 1. 1 is the probability that it's going to come up heads or tails. Not the probability of coming up heads. It's if somebody says, is it going to come up heads or tails? You say, yeah, right? Because you're sure that it's going to come up to be one of them. The probability is 1 that it will be one of the two outcomes. Now, here's another example. We'll start with the probability that your next birthday falls on a Monday. Because there are 7 days in a week, the probability that your next birthday will fall on a Monday is 1 out of 7, or 1/7. Now, we could go on to calculate the probability that your next birthday is on a Tuesday or that it's on a Wednesday, and so on. And the probability for each day would be 1/7. But that would give us 7 outcomes, and right now we're interested in examples where there are only 2 outcomes. So here's how we'll handle it. We'll say that the first outcome is that your next birthday is on a Monday. We could say that's P of A. Is that your next birthday is not on a Monday. There are 6 other possible days, so the probability that your next birthday is not on a Monday is 6 out of 7, or 6/7. And we call this probability Q. Q equals 6 out of 7. Now, if we add together P and Q, you know what we get. Take a look. So this is one of the most important facts about P and Q. P plus Q equals 1. Now I'll show you the other most important fact about P and Q. To find that fact, we're going to do a little algebra. First, we're going to subtract P from both sides. And that's when we get this formula. P plus Q minus P equals 1 minus P. So we've just taken the first equation and we've subtracted P from both sides. Then we rearrange the P's on the left side so they're together. We haven't really changed anything, we've just moved it around on the left side. And we get, you notice, we get a P minus P. Well, P minus P equals 0. So it's going to go away, and we get the next equation. Q equals 1 minus P. And this is the second most important fact about P and Q, that Q equals 1 minus P. Now, this equation turns out to be very useful. It tells us that if we know P, we can automatically get Q. That is, if we have P, no one needs to tell us what Q is. We can easily find Q for ourselves by subtracting P from 1. And this little equation, which looks so simple, turns out to be very useful. If someone tells us that 75% of passengers on the Titanic were men, we will call that number P. P equals 0.75. Well, then question is, what's Q? Well, we can easily calculate Q, the percentage of passengers who were women. As we just learned, Q equals 1 minus 0.75. It's 1 minus P. So Q must be 0.25. That is, 25% of the Titanic passengers were women. So here's a problem for you. If P is equal to 4.40, what is Q equal to? Now go ahead and figure this out for yourselves, and I'll give you a little time to calculate the answer. Okay, the answer is that Q equals 0.60. To find Q, we simply subtract P from 1. P is 0.40, so 1 minus 0.40 is 0.60. Next, we're going to talk about something called Bernoulli variables, which we'll be using frequently during the rest of this course. Bernoulli variables are named for the famous mathematician Jacob Bernoulli, who first recognized their importance and published mathematical explorations of their properties. You're going to learn some of the properties here. Bernoulli variables are dichotomous variables, or binary variables, whose values are either 1 or 0. For instance, here's data from 5 statistics students. The variable in the first column is the students' names. This is a categorical variable. It has 5 values. The value of this variable for the first student is Hiram. The value for the second student is Sarahi, and so on for all 5 students. The second column is student's gender. This is also a categorical variable, but it's dichotomous. It has only 2 possible values, either male or female. What do we call a categorical variable that has only 2 values? Yes. A categorical variable that can have only 2 values is called a dichotomous variable. Now, the variable in the third column is also for student's gender, but this time, instead of writing male and female, we write a 1 if the student is a male and a 0 if the student is a female. Now, this variable only has 2 possible values, 1 and 0. And so it's a Bernoulli variable. Because remember, a Bernoulli variable has values of either 1 or 0. So we started with the variable gender, which is a dichotomous categorical variable with values of male and female, and we have transformed it into a Bernoulli variable, which is a dichotomous quantitative variable. So we've gone from categorical to quantitative. And it turns out that this transformation is going to be very useful. For instance, we can't calculate the mean of the categorical variable for gender by averaging together 3 males and 2 females. We would end up with the ridiculous result that the average student is 3/5 male and 2/5 female. And it's impossible to even think how we could calculate the standard deviation of 3 males and 2 females. On the other hand, we can calculate the mean and standard deviation of this Bernoulli variable. And as I'll show you, the mean and standard deviation are not ridiculous. They do have a sensible meaning and are very useful. So as a beginning, I'd like you to calculate the mean for this Bernoulli variable. Just do the same thing you always do when calculating the average. Add them up and divide by the number of values. Then just sit quietly without saying well, never mind, I'm sure you're all sitting there. So please have patience. I'm going to give people about 30 seconds to compute this. By the way, if you need more time, you can always hit pause on this video. Okay, here it is. Down in the lower right-hand corner, the mean for this Bernoulli variable is 0.60. I hope that's what you got. Now you want to remember that number because we're going to see it again. Okay, now here's another question. What proportion of these students are males? I'm going to give you just a little time to think about it. What proportion? You might think it might be easier for you to think, what percentage of these students are males? Yes, the proportion of males is 3 out of 5, which translates into a proportion of 0.60 or 60%. And there's that same number I told you to remember, 0.60. Okay, here's another question. If we select a student at random from this group, what is the probability of selecting a male? Again, I'll give you a little time to think about this. There it is again. There's the answer in the lower right-hand corner, 0.60. The probability is 0.60. We can think about this using the frequentist definition of a probability. The situation that's repeated multiple times, or many, many times, is selecting a student in this group. The designated outcome is selecting a male. The percentage of times this outcome occurs is 3 out of 5, or 60%. So the probability is 0.60, or 60%. But of course, you noticed that we got 0.60 again for the third time. And this is one of the cool things about Bernoulli variables. First, the mean of a Bernoulli variable is equal to the proportion of ones in the sample. In this case, the mean was 0.60, and this told us that 60% of the individuals were ones because ones represent males in this sample. So 60% of the sample is male, but it's also the mean. In addition, the mean of a Bernoulli variable is equal to P, the probability the randomly selected group member has a value of 1. So the mean of a Bernoulli variable tells us the proportion of cases or individuals that are ones. It also tells us the probability of randomly selecting. So this makes our life easy when we're using a Bernoulli variable. So suppose someone asks us the mean of a Bernoulli variable or the value of P. We don't have to do any complicated questions. We only have to figure out what proportion of the numbers are ones, and that automatically tells us the value of P and gives us the mean. So in this example, what is P and what is Q? Just take a moment to think it through. Okay, here's one way to arrive at the answer. 60% of these individuals have a score of 1 on the Bernoulli variable. 60% is equivalent to a proportion of 0.60, so that tells us that P equals 0.60. And Q is equal to 1 minus 0.60. 1 minus 0.60 is 0.40, so Q is 0.40. So the answer is P is 0.60, Q is 0.40. Okay, so that covers how to find the mean of a Bernoulli variable. Now let's cover how to find its standard deviation. I'd like you to calculate their standard deviations. Now, at first, it may seem difficult, but think of it this way. You follow exactly the same steps as you do with any variable. First, you calculate the mean, and by the way, I think you already know the mean. Second, calculate the deviations of each score from the mean, then square those deviations, then calculate the mean square, the average of those squared deviations, that's also the variance, and finally take the square root of the variance to get the standard deviation. So I'm going to give you a little time to figure this out. See if you can get the standard deviation, then I'll explain how to do it. Okay, I'll give you about one more minute and then I'll give you the answer, show you the answer. Okay, I'm about to show you work this out for you, but if you haven't finished, you might hit pause on your video and then hit resume when you're ready, when you have your answer. Okay, now let's take a look at this. Over in the left hand under raw scores, we have our ones and zeros. Their sum is 3, and when we divide by the number of values, that's 3 divided by 5, that's 0.6. But that's the average of a Bernoulli variable, so that's p. The mean is 0.6. Next, we calculate the standard deviations. So we subtract at the top. The first score is 1, so we subtract 1 from 0.6, and we get, excuse me, we don't subtract 1, we subtract the mean from the score, so we subtract 0.6 from 1, and we get 0.40. Next, we have a raw score of 0, so we subtract 0.6 from 0, and we get negative 0.60. Now, at this point, most of our work is done because it's just repetition. The next time, we subtract 0.6 from 1. We already did that. That's 0.40. There's another one, 0.40. The deviation is 0.40. And finally, for a raw score of 0, we already know that the deviation is negative 0.60. So you notice what we're getting here are a bunch of values, and notice they're all equal to either q, 0.40 is q, or to negative p. And that's always true when we do a Bernoulli variable. We get a bunch of q's and negative p's. Now next we square them. Now we get even more uniformity and repetition. So the first standard deviation, we square 0.40 and we get 0.16. The next deviation is negative 0.60. When we square that, we get 36. And we do 0.40 and we get 1/6 and so on down the line. So we just get a bunch, only two numbers repeated again and again and again. And of course, they're all positive because they're all squares. Now, if we add them up, we get the sum of 1.20. When we divide by 5, because that's the number of values, to get the mean square, we get 0.24. And when we take the square root of 0.24, it's the square root of 0.24 is 0.49, and that's our standard deviation. Now, all of this is probably pretty familiar to you. Now, what I'd like to point out in the far right-hand corner is that what you're getting is q squared and p squared and q squared and q squared and p squared. And then when you add them up, you get 3 times q squared plus 2 times p squared, and then you work it out. And I've worked it out there with all those p's, and I work it out. And when you get to the bottom, and calculate their average. By the way, that's their average at the bottom. It's PQ. So the mean square is equal to PQ. And that's always true for Bernoulli variable. The mean is equal to P times Q. Then if we want the standard deviation, we just take the square root and we get the square root of PQ, which is the standard deviation. So we've just done what I call calculating the standard deviation of a Bernoulli variable the long way. By the long way, I mean we do it just like we do any other variable. We make a table, we calculate all the deviations, we get the squared deviations, and then we take their average and take the square, all that, you've done the standard deviation so much you understand that. But this is the long way. If we realize that no matter what P and Q are, the mean square is always going to be PQ, and the standard deviation is the square root of PQ, that tells us a short way. We didn't even have to go through all this work. So I'm going to show you the fast way to calculate the standard deviation of a Bernoulli variable. Here's the formula you use. The standard deviation of a Bernoulli variable is equal to the square root of P times Q. So you multiply P and Q together and then take the square root of the product. The standard deviation is 0.60, that's P, times 0.40, which is Q. And when we multiply those together, square root, we get 0.49. And that's exactly the same value we got doing it the long way. So this method really works. So here's a question for you. If P equals 0.70, what is the standard deviation? Use this formula to solve it, and I'll give you about a minute to figure it out. Okay, I'm going to show you the answer. If P equals 0.70, then Q equals 0.30, right? Because Q equals 1 minus P. P is 0.70 and Q is 0.30. We just do this math, that the standard deviation, if P equals 0.70 and Q equals 0.30 is 0.70 times 0.30. We multiply those together, we get a number, which is 0.21, and then we take its square root, and the square root is 0.458, which is approximately equal to 0.46. In other words, if we round, 0.458 gives us 0.46. And that little, between 0.458 and 0.46, you can see a little squiggly equal sign. That's a mathematical symbol that means is approximately equal to. So the little squiggly equal sign indicates is approximately equal to. Now, here's some data similar to what you saw earlier, but with a new group of students. I'd like you to calculate the mean and standard deviation for the Bernoulli variable, and I wanted you to do it the shortest and quickest way you can. I'm going to give you 90 seconds, and after you get your answer, I'll give you mine so you can check against it. So calculate the P and the standard deviation of the yeah, standard deviation the quickest way possible. Time starts now. Okay, so let me give you the answers. 0.80. Now, to calculate this, you first notice there are 5 students, and 4 of them have ones, have values of 1 on the Bernoulli variable. This means that 80% of the values are ones, and therefore p equals 80% or 0.80. The mean is equal to p, so the mean is also 0.80. For the standard deviation, you need q. If p is 0.80, then q must be 0.20. So for the standard deviation, you multiply 0.80 times 0.20, that's p times q, and calculate the square root. And the result is 0.40. So it's important that you memorize and practice the equations for the mean and standard deviations of a Bernoulli variable so you can do it very quickly. All the material covered in today's lecture is also covered in your book with exercises, and you can get more practice there. In the coming weeks, we'll be using these formulas many times, so you want to become very familiar with them and very comfortable using them. Okay, so that finishes the presentation on probability, and I remind you that you need to take quiz 7. Quiz 7 is scheduled for the same day that this lecture is scheduled, and it's in your syllabus. And be sure to go on to Blackboard and take quiz 7 on this day. It's not a delay of 2 days. So for some of you, this you need to take quiz 7 on a Tuesday. Some of you will be taking it on a Wednesday. Okay, thank you very much. If you have any questions, be sure and write your TA or your instructor. And it's been a pleasure talking to you about probability. We'll see you at the next lecture, which begins to talk about political polls and surveys.